Sorry, yeah, sorry. Somehow I mute myself. So our last speaker is from Dr. Shafayat Hossain. Apologize if I didn't pronounce your name right. And Hossain is from Princeton, and he's going to give a talk on tunneling into quasi-1D materials. Please go ahead. Thank you.
Thank you for the introduction. Let me share the slides. All right. Okay. Can you see my screen?
Yeah, looks good.
Great. All right. Good afternoon. So I'm Shafayat, a postdoc at Princeton University in Zahid Hassan's group. I will briefly talk about, I think, two of the quasi-1D materials that we have studied, given we have time. So here is the outline of my talk. I will talk about some quasi-1D materials that interested us to start our STM explorations and how we measure these materials in STM. And then two results, one on the quantum spin Hall edge state at room temperature observed in alpha bismuth bromide. And if time permits, I'll talk about edge state in a charge density wave compound in another quasi-1D material, tantalum selenium iodide. So let's start. So, from application perspective, these quasi-1D materials are very, very interesting because unlike these 2D materials where you have covalent bonds within each of the layers, in quasi-1D materials, you have very weak bonding, say between one chain to the another. So in principle, one can synthesize even in 1 nanometer by 1 nanometer scale thread, which will be very useful for scaling down the interconnects or channels of the electronic devices. And there are many, many such materials. Now, from the physics point of view, there are very, very interesting physics in quasi-1D materials because it has even more quantum confinement than the our traditional 2D materials, and it has intriguing quantum effects. If we look into the literature, there are these bismuth halides, bismuth iodide or bismuth bromide, which are topological materials. There are even coexisting strong and weak topology in another quasi-1D materials, the tantalum nickel tellurium 5. There are quasi-1D superconductors. You can apply pressure and make this bismuth bromide superconducting, or even tantalum tellurium 4 superconducting. And there are some quasi-1D superconductor pattern compounds with intriguing magnetic structures and so much more. So to explore these materials, we resort to scanning tunneling microscopy technique. And this is a very powerful technique to study a new quantum material because it has an excellent spatial resolution. One can image the atoms. And it also has an excellent energy resolution, which gives us information on the local density of state and also some information on the electronic band structure. And we know that this STM, the invention of the STM was dated back around 1983, and it got Nobel Prize in 1986. So what STM does is we have an atomically sharp tip, and this atomically sharp tip is placed very, very close to the sample surface, and then electron can tunnel between this tip and sample. And if we measure this tunneling current, keeping the current fixed, it gives us a topographic image with an atomic resolution, kind of like this. And also, we can take a derivative of the tunneling current, which gives us this dIdV. And this dIdV is a convolution between the local density of state of the sample and the tip. And if the tip density of states is as simple as this, then all it remains is the dIdV is proportional to the local density of state of the sample. So just by measuring this DIDV gives us information on the local density of state. And as I said, that STM offers excellent energy resolution. We can learn about the spectroscopy in great detail. For example, here we see a gap where tunneling is 0 in a certain range of bias. All right. So we have 2 scanning tunneling microscope in our lab. One is an Unisoku, which can go down to helium-3 temperature. We primarily use it for low temperature measurement. And here we have a vector magnet, 922 Tesla. So we do mostly field dependent and low temperature measurement in this STM. We also have another STM, which is good at high temperature, so we can control temperature very precisely, and it's from Omicron, and we can go up to room temperature in this system. All right, so we explored these Quasi-1D materials in those 2 of these STMs, depending on what we want to do. For example, temperature dependence, we choose one STM, for field dependence, another. Now, this Quasi-1D material, they're needle-like, understandably. So this poses a little bit of challenge in finding a flat, clean crystal. So we thank the sample growers who provided us with pretty large samples, I would say, like here or here. So we glue a post and then we cleave in high vacuum and expose the fresh sample surface. And then we load the sample in our STM. So now let's look at our results. So we start with the quantum spin Hall state at in bismuth bromide at room temperature. The work came out in 2022 in Nature Materials. So room temperature quantum phenomena has always been interesting in the physics community. So I would say the only macroscopic quantum phenomena in room temperature reported so far is the integer quantum Hall effect. High magnetic fields require like 45 Tesla, or even here 29 Tesla. There were also a controversial report of room temperature superconductivity, but it required pretty high pressure, 267 gigapascal. So here, this quantum spin Hall state, which I'll talk about, it does not require any such extreme conditions. It can be realized in 0 magnetic field and, of course, in ambient pressure. So quantum spin Hall state features to counter-propagating or helical edge states running along the sample edges. So these edge states are dissipationless. And this edge states resides within the bulk gap that comes because of the band inversion, bulk band inversion. So the theory came back in 2005, and then was realized in mercury telluride quantum wells back in 2007. And there are some other materials later on to realize this quantum spin Hall state, like bismuthine or tungsten ditelluride. So one experimental observable to distinguish the trivial insulator and the quantum spin Hall insulator is the presence of an edge state. For example, here in trivial insulator, there is this bulk gap, but there is no edge state. Whereas in the quantum spin Hall system, there is bulk gap and there is this helical edge state. And this edge state we can measure in STM, and which is what we have done here. So let's talk a little bit about our material platform where we do this. It's alpha bismuth bromide. It's a Quasi-1D material. So it has this bismuth bromine chains running along the B axis of the crystal. And theory says that it has a large bulk gap and quantum spin Hall edges. We know this back from 2014. And more recent ARPES work shows a topological boundary mode, but in the absence of real space imaging, it's elusive whether this boundary mode is from side surface or the atomic step edges. So towards that motivation, we started real space imaging of the bismuth bromide. So first, we look into TEM data, this transmission electron microscopy. Looking at the cross-section, we see AB stacking, interlayer AB stacking. And this is important because with this, we can look at our surface, look at the top view, and distinguish which layer we are seeing. Is it A or B? For example, here, the scanning tunneling microscope image shows the A layer of the clipped surface. We also see the B layer, which I'll show you later on. All right, so after finding a clean surface, then we focus on spectroscopic measurements. And what we find is there is a large insulating gap of 260 millielectron volts. This is consistent with the ARPES data and also roughly consistent with the first principle calculations, although first principle calculations predicts a slightly larger gap. So after finding this large insulating gap, the goal is to see whether this gap is topological or not. So towards that end, we search our crystal extensively and then find an atomically sharp monolayer step edge. So since this is a monolayer in an AB stacked material, one side of the monolayer edge is A-type surface and another side of the edge is the B-type surface. If we zoom in, we again see this A-type and B-type surface. So it breaks the mirror symmetry along the A-axis. All right. So now what we can do is we can place the tip, STM tip, far away from the edge. And then we see a large insulating gap. And we can also place the tip right at the edge. And we see that there is no gap. It's actually, there is an in-gap state, gapless in-gap state right at the edge. So there is a edge state at the edge, and the bulk or the surface here is gapped. So this is consistent with the topological bulk boundary correspondence. Now we can do a spatially resolved conductance map throughout this region, and that's what we do here. And what we find is at Fermi level, at the 0 millivolt bias, where the surface is gapped, the edge is excited. So there is an edge state right at the Fermi level. Now, we can also measure the localization length of the edge state, of course, as a function of distance. And we see that the localization length is about 2 nanometer, which also matches the first principle calculation on ARPES reasonably. And there is this exponential decay of the edge state on the crystal side of the sample. All right. So now that we have seen an edge state, now how can we tell whether this edge state is not trivial? It's indeed a quantum spin Hall edge. One way is to check the time reversal symmetry protected nature of the edge state. So what we can do is we can apply a magnetic field, which will break the time reversal symmetry, and we can see how the edge state spectra evolves. So here we do just that. At 0 Tesla field, we see, of course, there is a gapless edge state. And as we apply magnetic field perpendicular to the AB axis of the crystal, we see that the edge state starts to show a gap. And the gap becomes more pronounced at higher magnetic fields. For example, here at 8 Tesla, there is a clear gap. So we can tell that when we apply a magnetic field, energy gap develops at the edge. And also, we can do a similar conductance map, as I showed you before, as a function of magnetic field. And we see that the edge state spectra become suppressed at the Fermi level as we apply higher and higher magnetic fields. So this is all consistent with the Z2 topology because the edge state is getting gapped out at the Dirac point when the time reversal symmetry is broken, which we do by applying a magnetic field. All right. Since we have a vector magnet, we can also apply magnetic field along different crystal directions. For example, here we apply the magnetic field along the B axis of the crystal, so along the edge direction. Now, what we see is even if we apply a magnetic field along the edge direction, there is still edge state. If you see here, the edge is still excited. Versus if we apply a magnetic field perpendicular to the edge along the A-axis, the edge state becomes suppressed. So this is again clear from the differential spectra and the IDV spectra. So when the magnetic field is parallel to the B-axis or parallel to the edge, there is still gapless edge state. But when the magnetic field is perpendicular to the edge, then there is a gap, small gap. So this is because when the magnetic field is parallel to the edge, it just shifts the edge state in momentum space. So it does not gap out. But for the perpendicular case, there is a small gap that develops. So this is again all consistent with the time reversal symmetry breaking nature of the edge state. So our next evidence is based on the hybridization of the edge state. So specific to bismuth bromide, it has this unique AB interlayer stacking where the inversion center is not in the bilayer, so it's in the monolayer. So it leads to two types of edges. So one is the type 1 edge on the left side, so where the facing angle is greater than 180 degrees. And there is another type of edge, type 2 edge here. The facing angle here is less than 180 degree. Now we know that the hybridization of the quantum spin Hall edge is destructive. So when the facing angle is larger, then the hybridization is weak. So the edge state survives. Versus when we have a smaller facing angle, there is a stronger hybridization and the edge state becomes weaker. So this is a building block of a higher order topological insulator phase in this bismuth bromide compound. So eventually, for example, here, after all the hybridizations, there are two helical hinge modes in the top left and the bottom right corner. And all of this happens because of this inversion asymmetry in the AB layer. All right, so now experimentally, we need to find these two types, this type 1 and type 2 edges. Of course, it required an extensive searching because it's rather unlikely to find them very nearby. But fortunately, we found that, and then we have these two nearby type 1 and type 2 AB edges. And here what we can do is we can first place our tip exactly at this edge here with the red dot, and we can do a spectroscopy, and we see that there is a clear edge state. Versus if we place the tip on the other edge, on the blue one, we see that there is no edge state. The spectra is gapped. So the type 1 and type 2 AB edge show a dramatic difference in the nature of the edge state. So for the type 1, there is edge state, and for the type 2, there is suppression of the density of states. So this is an evidence for a destructive hybridization of this quantum spin Hall edge. We can also see this hybridization in the conductance maps. So here, for example, at Fermi level, we see only the type 1, or here the right AB edge shows the edge state. Left one does not show a clear edge state. And even in another in-gap bias, minus 75 MeV, same thing happens. Only the right one, the type 1 AB edge show the edge state. So this is a building block of the higher order topological insulator for the bulk phase. All right, so with Fan, we have some calculations which matches the experimental observation. So from the edge projected band structure, where there is an edge state where the Dirac point is rather close to the Fermi energy, and there is a very large bulk gap. Although there are some differences, because here the Fermi level is right in the middle of the gap, versus in the experiments it's more towards the negative side. All right. And also Fan's group did some calculation for the higher order topological insulator cases for 2-layer or 20-layer samples. There are, of course, the helical hinge modes, the red ones, and also there are the side surface states. All right. So all the data I have shown you so far, they're all taken at 4 Kelvin. So now, finally, we do the temperature dependence. So we see that if we increase the temperature from 4 Kelvin to 100 Kelvin, 200 Kelvin, and even 300 Kelvin, there is still a bulk gap. And also there is this in-gap edge state. And they all survive even at 300 Kelvin. And importantly, the Fermi level always stays within the gap. So there is edge state then at 300 Kelvin within the bulk gap and in the Fermi level. This can also be seen in the conductance maps. At all 3 temperatures, there is an edge state at the Fermi level. Now that I've shown you the temperature dependence, it shows that, of course, there is a room temperature a quantum spin Hall edge state. We can also do more measurements. Say, for example, we can take a line spectra perpendicular to the step edge, and we move the tip away from the edge and then pass the edge and then go to the other side. So away from the edge, there are these gapped spectra at 300 Kelvin, and then right at the edge and close within the decal length, there are gapless edge states. So it gives us confidence that, yeah, we see a room temperature quantum spin Hall edge state. And so the key takeaway would be there is a quantum spin Hall edge state at room temperature and in the Fermi level, and we can substantiate its Z2 topological nature with the magnetic field dependence and the quantum hybridization. So the outlook, well, we have been trying to realize a room temperature quantum spin Hall effect, but luck has not been very generous to us. So this is a very long project, and we have made some devices, but still not too much success. And another dream is to do a gate dependence and see if we can induce a superconductivity, kind of like tungsten ditelluride. And of course, there are more into the future. Eventually, we would love to make a device that realizes a topological transistor, and of course, with higher order topology, the design can be made very rich. All right, so I would like to thank all my collaborators at Princeton. The samples came from, the STM samples came from Jianwei Huang and Wu Yao's group at Beijing Institute of Technology, and the theory support came from Fan at Dallas, and also from Tyrong. So how long do I have?
Let's see, you have 20 more minutes.
Beautiful. Okay, so then I can move into my second part. All right, great. So the second part is on the observation of the edge state, which is coupled to the charge density wave in tantalum selenium iodide. All right. So tantalum selenium iodide is a very exciting material platform. For us, it's the only known platform that has a wild semimetal to a charge density wave transition. And this is also an axion insulator candidate. But proving an axion insulator might be challenging, which will require, of course, this quantized bulk magnetoelectric coupling coefficient of pi. And also there is another paper which suggests that it should have a gapless time reversal symmetry protected surface state, topological surface state. So from the literature, there were evidences for pieces of evidence for axion insulator like behavior, some paper back in 2019. So here we explored this material in STM. So this is also kind of features a quasi-one-dimensional structure with chains running along the c-axis of the crystal. So we start with transmission electron microscopy image and along the growth direction, and we see these sets of parallel chains running along. Now, when we cleave the sample for STM, what happens is, for some reason that we do not know of, 50% of the iodine atoms goes away. And eventually what we have is a nearly square-shaped lattice of iodine on the surface. And then what we do is, if we take a large-scale topographic image, we have this nearly square iodine lattice, and we see a clear charge density wave, a unidirectional charge density wave, for nearly 45-degree with respect to the c-axis of the crystal. And this charge density wave also reproduces in a DIDV map, this conductance maps. And we can also, of course, extract the charge density wave wavelength from these measurements, which is about 12 nanometer. And it's consistent with the prior X-ray neutron scattering measurements. And spectroscopically, this charge density wave state features a very large insulating gap. This is about 550 millielectron volts. So this is a very large gap. And this gap is also consistent with this large gap is also consistent with the ARPES data, which of course probes only the occupied side with half of it. So this is another very large gap system, and which is also modulated by the charge density wave period. Here, for example, it's modulated by around 12 nanometer, very close or almost equal to the charge density wave wavelength. So after characterizing this charge density wave state, then we would like to know what happens right at the edge. So to do that, we again found a very clean atomic step edge, a monolayer step edge, which runs along the c-axis of the crystal. And then we can do a detailed spectroscopy. So we start with measuring the spectra away from the edge, for example, here. And then we see a very large gap, about 550 MeV. And then we place the tip close to the edge, and right at the edge, we see a gapless state. So I would like to point out that these measurements are done at 160 Kelvin. The reason is, since this is a very large gap system, at lower temperature, it's rather difficult to get a stable tunneling. So maybe that's why the edge spectra looks a little bit broadened. So, all right, we can also do conductance map measurements here. And we see that there are edge states very weak at the Fermi level, and then become stronger at finite voltages within the gap. And of course, at outside of the gap, the edge state is no longer there. It's rather suppressed. So, all right. So here we see a gapless edge state in the charge density wave state of this tantalum selenium iodide. Then we can do a temperature dependence measurements and see how this edge state is linked to the charge density wave state. So first, let's look at what happens if we look at the surface. We image the surface as a function of temperature. So at 160 Kelvin, there is charge density wave. Also, there is clear charge density wave peaks. And 250 Kelvin, they're still there. And at 280 Kelvin, the charge density wave is gone. And there is no, of course, there is no charge density wave peaks. So this kind of matches with the expected charge density wave transition at around 260 Kelvin. So we see this charge density wave disappearing in STM at high temperature.
Can I ask a question here? Are this
Yeah.
image taken at the same area, or is it's different? It seems that those point defects.
It's a different area. You're right.
Okay.
Mhm.
But how come those point defects is more obvious at lower temperature compared with higher?
There are still point defects, but again, the I would say the resolution or the fidelity of the picture is lower at higher temperature, because it just becomes much harder to take atomically resolved data at much higher temperatures. But you're right, they are all taken at different temperatures, different regions for the surface. We could only keep our edge fixed. So what we did is, I will show you later, we could keep the location of the edge fixed, but surface very hard, because there are many defects. So finding the exact same surface is very difficult.
I see. Thank you.
Welcome. All right. This charge density wave state disappearing matches well with the expected charge density wave transition temperature from transport measurements. All right. So then what we can do is we can look into the temperature dependence of the edge, see what happens as we cross the charge density wave transition. So at lower temperature, below the TCDW, there is this gap, bulk gap, and also a gapless edge state. And as we raise the temperature, eventually, the edge state is getting weaker and weaker. And finally, at above the TCDW, or the charge density wave transition temperature, the edge state becomes weaker than the bulk, and basically the bulk becomes gapless. So this is consistent with what is expected from tantalum selenium iodide, that there is a wild semimetal state above the charge density wave transition. So it should behave as a semimetal. So this is rather consistent. In brief here, what happens is as we raise the temperature up above the charge density wave transition, the gap and the edge state both go away. And this can also be seen in the conductance maps. So if we take a conductance map below the charge density wave transition at 250 Kelvin, there is edge state at Fermi level. And for example, there is no edge state, of course, away from the gap at minus 0.4 volt. And if we go away from above the charge density wave transition temperature at Fermi level, then there is no edge state. So it appears that the edge state is linked to the charge density wave, because they show a similar temperature evolution. Now, the question is, how do we tell, again, how do we tell that the edge state is non-trivial? So one obvious thing we can think of from the study of bismuth bromide, that we can just apply a magnetic field and see what it does. Unfortunately, in this case, at such high temperature, we cannot apply a magnetic field. We would love to do that, but we cannot. But fortunately, there is another way. So we collaborated with Titus Newport's group to Zurich on the theory side of this. And they suggested that, if you look at the edge, it should show an oscillation of the density of states. It should show an oscillation of the density of states, and the periodicity of that oscillation should be square root of 2 lambda CDW, which is just the projection of the lambda CDW along the edge, because it's 45 degree with respect to the c-axis. The charge density wave vector is about 45 degree. So the edge state should show such an oscillation corresponding to the charge density wave. So to do that, we looked into a larger region. So we looked into a larger topographic region here, and then we do a systematic DIDV maps at different biases. And at first sight, it's not obvious that there are any oscillations. But if we look closely and just plot the line spectra along this green line as a function of position, we would see that indeed there is oscillation with a sinusoid here. The small peaks, they are corresponding to the atoms, but there is a long wavelength oscillation superimposed to it. But of course, the magnitude of this or the amplitude of this oscillation is not too strong. For example, here it's say 0.082 to 0.088. So there is a large background, and then there on top of it, there is this oscillation. But most important thing is, yes, there is oscillation in the IDV along the edge. And this oscillation persists in all these in-gap voltages. The oscillation periodicity match reasonably well with the square root of 2 lambda CDW. So these purple curves are sinusoids with square root of 2 lambda CDW wavelength, and you see they match reasonably well. We can also take a Fourier transform of the raw data, and we mark the position of this square root of 2 lambda CDW in the Fourier transform with this orange line. And we see that there are in this long wavelength peaks at all these biases, and it matches very well with this expected value. So this is an evidence that there is a strong connection between the charge density wave and the edge state within the charge density wave gap. Another thing is, if we look into the peak positions, so there are these long wavelength oscillations, and there are these peaks. So we can plot all these peak positions as a function of bias. And we see that these peak positions move in positions as a function of bias. So this is an indication of a pseudo-spectral flow along the edge. And again, this is also consistent with the non-trivial nature of the edge state. Again, from the Fourier transform, we can also extract the Fourier transform phase and then plot it as a function of bias, and we see again this movement of the peaks. So again, we have then two supporting evidence for the non-trivial nature of the edge state, which is this pseudo-spectral flow, and also this oscillation, this periodic oscillation that matches with the lambda CDW projected along the edge. All right. So in summary, we see an edge state in the charge density wave phase, and this is rather robust, again, survives even at 250 Kelvin, below the charge density wave transition temperature. Another interesting thing I want to mention is that I've shown you that the surface is highly gapped. It has 550 MeV of gap, and it's a hard gap system. There is no density of state within. So as I said before, that the action insulator interpretation perhaps entails a presence of a topological surface state, which is not seen in our case. So it's inconsistent with the interpretation. All right. Before closing, I would like to mention one other thing. As I mentioned here, the charge density wave gaps out this wild semi-metal phase. The question is, resulting phase, which has this gap, delta CDW, what is the topological nature of the gap? That's still a big question to us. We do not know what's the topological nature of it yet, because there is no calculation, no theory calculation in the presence of a charge density wave state in this material, which can predict what's the topological nature of it. The challenge is just the long wavelength of the charge density wave phase. So here we see an edge state, but we still are not confident about the topology of the system. We have some calculation, and I would not go too deep in it. So it suggests that here it's a Chern insulator, which has a Chern number of ±2. Here it's not perfectly a 1D system. It's rather a 0D that oscillates along the edge. So with that, I think I will conclude. And the outlook would be, we want to understand what's the topological property of this compound, tantalum selenium iodide. Hopefully, we'll be able to answer it in near future. All right. So I would like to thank all the collaborators in this project. The sample again came from Beijing, and also Max Planck from Claudia's group, and theory support is provided by Titus. So with all that, I would like to thank and conclude my talk. Thank you for your attention.
Thank you, Shafayat, for your excellent talk. And now we open for questions.
Thank you for the talk. May I have a question?
Go ahead.
So how large is the CW unit cell?
Okay. CDW here is about 12 nanometer. Let me, I hope it did not crash. Okay. All right. I think this would work. So it's about 12 nanometer, and the iodine lattice is roughly 1 nanometer. So inter-iodine atom distance is about 1 nanometer. So yeah, it's
okay. Is it commensurate with the original lattice?
Okay, that's a hard question. So I do not want to comment on it, but you know, the interatomic distance is about 1 nanometer, and then what we have here is the 12 nanometer periodicity. But from this 1D pattern, to me, it seems rather hard to commit to a commensurate versus incommensurate. So we do not really talk about it here.
Okay. So from the real space picture, is there anything special about, is there any hints about why the 45 degree is so special? I mean, the CW direction.
That's an excellent question. Well, what we know is the 45 and minus 45 degree are both possible. There is another paper that reports, I think, also minus 45 degree. But other than that, why 45? I do not know. I think a good DFT calculation would really help. But as I said, it's very, very challenging.
Okay, so it's almost exactly 45.
I would say so, yes.
Okay. Oh, one last question. Is there anything you can say about the role played by the phase of the CW order parameter? Is it important here?
Phase of the CDW.
Order parameter, yeah.
Again, that's as I said, from the theory point, we do not know almost anything about it. The only thing that we know about is there is a large gap, there is an edge state, and there is some oscillation that corroborates with the charge density wavelength along the edge. That's all we can say so far. We tried to motivate our theory collaborators to do some theory calculations, but it's very difficult. So other than that, I do not even know about the charge density wave order parameter here. I do not know what to comment on in this case. I think it's all open question.
Okay, thank you very much.
Thank you.
Andrei, please, and Jenny will be the next.
So I just have a quick question about your, so you said it's something is inconsistent with an axion insulator in the last but one slide. Can you go back to that slide?
Yes. Please. Yes, here.
So what's inconsistent with an axion?
So this is inconsistent meaning, let me probably go all the way up. Okay.
Well, you wrote there in the sentence what's inconsistent.
Yes.
So if you can go through that sentence.
I think this is good.
Okay.
Yes. So there is a paper that suggests that there is a time reversal symmetry protected topological surface state in an axion insulator. So given that that paper is correct, our data would be inconsistent. So we do not see any gapless surface state in this material.
I mean, okay. I mean, what you wrote there in the last slide is just that's what I'm a little bit confused about. The axion insulator is just a z equals to 2 invariant. It's got gapped surface states and a hinge state. That's the definition of an axion insulator. So no surface state in presence of edge state is actually what you'd expect from an axion insulator, not from a time reversal invariant one. That's not what people really refer to as an axion insulator. But that sentence that you wrote there is not correct. In other words, it should be, you can say it's inconsistent with the time reversal invariant axion insulator, but the axion insulator is defined, just, take a TI, this Shui experiments, take a TI, put magnetic, that's an axion insulator, it's not a dynamical one, but it's got gapped surfaces and gapless edge mode. So you should clean up that sentence right there, or add some words to it, because that was what I'm confused about.
Sounds good. Yes. So then I understand. Here it should be the time reversal symmetry protected.
Yeah.
Yeah.
Okay. Very good. Thanks.
Yeah. Great. Yeah. Thank you.
Jenny, go ahead.
Sorry, I'm muted. Yeah, so I'm muted. Okay, yeah, so really interesting, really interesting talk. Actually, I have a very simple question regarding the first part of the talk on the bismuth iodide. No, actually, just for your line, when you did the measurement on the edge, it seems to always a small zero bias dip. What causes that?
We think it's because of a Tomonaga-Luttinger liquid, but we have not done a systematic temperature dependence on it to to do the proper scaling analysis to do this. Usually, such a dip has been seen in these Tomonaga-Luttinger liquid states. It can also be seen in bismuthine, where it was analyzed systematically.
Okay, it's not related to some, for example, phonon blockade or something like that.
Phonons, here I cannot really comment on it because we are not particularly sensitive to phonons. So from here again, that's what I can tell. This dip is usually associated with those Tomonaga-Luttinger liquids. But of course, I cannot rule out phonons. It's just experimentally, I cannot comment on it.
Okay, all right. Yeah, no, thank you.
Thank you.
Great. Although we're approaching the 5:05, I have one last question about your outlook for the bismuth bromide. So I guess I'm wondering what preventing you guys from getting those devices, or what are the difficulties? Are you doing cleaving to monolayers or
So
flakes?
what we are doing is exfoliation.
Okay.
First of all, this is a quasi-1D material. So getting a uniform large area flake is rather difficult. So imagine we are aiming for a monolayer. So we need a monolayer where you have the interlayer, not interchain coupling is still enough to hold a monolayer all together. So we have seen that there we get some wire, very thin wire, but when we measure across, we do not get anything. Then we realize that maybe the coupling between two neighboring chains is too weak. They basically fell apart. So that's one thing, just the structure itself. The second thing is the extreme air sensitivity. We do everything in glove box, of course. So, and then when we take out just for the measurement, at some point it does not work. So the air sensitivity gives us a lot of trouble. So say we make 20 devices, maybe one work. That's kind of the yield rate. And the last thing is the control over the Fermi level. We do not really know where the Fermi level is in an exfoliated flake. Then we have to gate them, of course. There is no other way for us. So we try to gate them, and as soon as we apply some gate voltage, it's most of the time that the sample burns. We do not know why, but we have learned that the insulating samples actually do that. There are many cases where the insulating samples die very quickly with the gate if there is some small leak or something. So
sorry. Yes, just I was going to. I'm curious, what method you use for contacting them?
It's a usual gold.
Just gold with no sticking layer? Or
it's a palladium gold.
Palladium gold. Oh, interesting. Yeah, thanks.
Thanks.
All right, thank you for the nice information.
Mengke, sorry, I don't know how to raise hand over here. Actually, I have questions.
Oh, okay, go ahead.
Follow up with Jenny's question. So can you go back to your hinge, the AB two different edge states that plot, which Jenny have. So no, just next one, your experimental part. So I might be, you might talk about it, I might be miss a point. So you have monolayer and bilayer, right? How you difference with this monolayer, bilayer from STM?
Okay. two ways. So first, that is seen here. This has the AB stacking, right? So before in monolayer, one side is A, another side is B, which we can see clearly from the STM surface measurement, just the topography. For bilayer,
No, how you know it's monolayer? It's not all
Yes,
layer, or it's
yes, I'm coming to it.
Mhm.
And here we have all A. So that is the first. And the second thing is we can take a height map. Let me see if I put a height map here. Just a second. Just a
the
second.
slide is gone.
Yes, I'm trying to open up a height map. We can measure the height also from the topography. Let me see if I have one here.
Right, you take a line cut probably, right? Take a
yes,
line cut and
yes.
you see how high is the steps, whether corresponding to one atomic thing or bilayer atomic
Exactly.
thing. Yeah, you can tell.
I am trying to pull out something that's that would be best. All right. Good. Okay. Yeah, I can probably share this. And let me see. Okay. Great. Can you see my screen?
Yeah. We can say it.
So we can just take a line profile perpendicular to the edge. So we have the topographic image, and then we take a line profile, and then we know the height. Of course, I mean, first we need to have it calibrated. So after calibration process, this height gives the exact height. So for example, here, this is a monolayer step edge.
Yeah,
So
this
if
is
yes, please.
this is understandable. As Mengke mentioned, when you mentioned about this, it's easier for me. But can you go back to your slide again on that
Yes.
particular slide?
Yes. Share. Okay. Maybe
In that particular one. No.
actually, let me go back here. Okay. Here.
Yeah, this one. Yeah. So in this way, when you have your AB, right? AB type H and your different type of type 1 and type 2 edge, they are not necessarily monolayer to the bilayer. Am I correct?
They're all bilayer, like this. So type 1.
Then how you differentiate from your experimental, except your DIDV curve, your 29 slides, right? Except that one, are you able to tell really? Are you differentiated really mainly by your DIDV curve on the slide 29, the middle of that figure?
I am not sure I understood the question.
So how you differentiate this a different type A and type 1, type 2?
I see. So type 1 and type 2, for example, if you look at the schematic here, so there are only these two possibilities, right? It has to be either type 1 or type 2. Now, well, which one is type 1 and which one is type 2? That is, again, that needs to come directly from the DIDV. Or
have to come from the that's my question. That's my question, more or less. Yeah. Okay. And so can you go back to your slide 27? 27. So see 27, when you have this implemented field, right? I'm not talking about the one at the edge, the one away from edge. Looks like when you apply field, you do say the gap is slightly decreasing, right? The one, the other curve, not the red one, the color one. But when you go back to your slide 25, so if I'm not mistaken, when you apply the field under this one, the gap somehow opened, get bigger at 4 Tesla, and then get decreased again at 8 Tesla. Am I correct?
Well, I think there are a couple of things. First is we did not really measure the gap magnitude in detail. I need to check that. And also there are some features which we think may be related with the Landau levels and so on. But the gap magnitude,
but here, definitely from 0 to 4 Tesla, your gap in 8 Tesla, you can talk about all the other features, right? From your 0 to 4 Tesla, it's pretty clean. Your gap is open, it is bigger, right?
I think so, but I still need
And
to
on the other
define.
hand, when you have the implant, the gap is typical, the gap is getting smaller, right? I think a 27 slide is to looks more convincing to me, but this one, I don't know whether you observe the difference here and what's the cause of this.
Yeah, to comment on the magnitude, I need to do this proper analysis at what point the spectra leaves 0.
Okay.
I've not done that.
Okay.
But by eye, you are right. By eye, it appears that at least in this slide 25, the gap here appears to be larger.
Okay, thank you.
Thanks.
All right, great. Thank you, Shafayat, for the nice and interesting and fruitful discussions. We should probably close here, and thank you everybody for joining today's session. And then we'll have another session in 4 hours. Yeah, we are looking forward to see you in 4 hours. Have a good dinner, everybody, or lunch.
Thank you, Mengke.
Thank you, Bing. Bye-bye. Bye, everyone.
Thank you.